So, good morning, everybody. Welcome to our lecture today. So, we are already quite progressed in the semester. This is, I think, lecture 5. So, to give you a bit of a roadmap, what is coming up, or what is the plan for this week and next week. This week, we will finish this Unit 2. We will start Unit 3, do approximately the first part of Unit 3, and then next week we will finish Unit 3. Okay, so we have lecture this week, we have lecture next week, then there will be reading week, and in the week after reading week we will not have lecture. Okay, so we have 2 lectures, today, next week, and then there is a 2-week break. Okay, I showed you the schedule at the beginning. So that means that actually the content for the midterm will stop next week. So the midterm will be about all the content that we did in the lecture before the reading week. Okay? Good. So last week we started to become a bit more theoretical. We talked about portfolio statistics and we started to talk about portfolio selection. Okay? So remember, portfolio statistics, that was relatively general statistics, somewhat related to portfolio context and to investment context, but still relatively close to what you know from your statistics courses. Now we are going more directly into the investment universe. Okay? So the question that we talked about at the very end of the last lecture was how we should invest or how we should choose an optimal portfolio in a world that is greatly simplified. And in this greatly simplified world, we only had 2 assets. We had a risk-free asset and we had 1 risky asset. So that was our highly simplified world. And in this world with only 1 risky asset that we called the portfolio P and the risk-free asset that we typically call F, we developed some formulas. Okay? So in one of the formulas, the first one was that the expected return of C, and C here is the complete portfolio. So that means the portfolio that is the combination of the risk-free asset and the risky asset, is 7, which is the return of the risk-free asset, plus Y. Remember, Y was the fraction that we invest in the risky asset, times 15 minus 7. And this 15 minus 7 is nothing else than the so-called risk premium. So this is the return or the expected return we get from investing in the risky asset minus the risk-free rate of return. Okay? So this is the expected return of the complete portfolio. When we think about the risk of the complete portfolio, remember that actually quite a lot of the last week, quite a lot of the time in the last lecture, we talked about the measurement of risk in a portfolio context, because we said it's not just the weighted average, right? We have to consider this covariance between the assets. In this special case, however, we have seen that actually the risk of the complete portfolio is nothing else than the risk or the standard deviation of the risky asset times Y. This is the special case if we have a risk-free asset and a risky asset in the portfolio. Only in this case, this formula holds. Why is this the case? Well, because first of all, quite obviously, the risk-free asset has no risk. That is how it is defined, right? It has no variability. Or if you think about it in this table structure that we used at the very beginning last week, in every future state of the world, the risk-free asset will deliver the same return. It's always the same. So there is no variability. And the second thing is that we can safely assume a correlation of 0 between the risk-free asset and the risky asset. Okay? Because the risky asset moves in some states of the world, like if we are in a boom, the risky asset will have a very high return. And if we are in a crash, the risky asset will have a very low return. The risk-free asset will always have the same return. So it's quite reasonable to assume that the correlation is zero. Okay? So of course, in reality, the correlation would not be exactly zero if you measure it, but it would be somewhere close to zero. And if that holds, we get this expression that the risk of the complete portfolio is the risk of the risky asset times y. Okay, so the next slide shows the proof, but we don't have to go through that now. And then we developed this formula that the expected return equals 7 plus 8 divided by 22 times the risk. So this formula shows you the relationship between expected return and risk. And as you can already nicely see here, this is a linear relationship. So if you plot that, that must be a straight line. The intercept of the line is 7 and the slope is 8 divided by 22. Right? So in the last step, or the last thing we did last week was to look at the picture. Sorry. To plot that. So let's do that again, but let's do it in a more gradual and interactive way. So we are still in the world of one risk-free and one risky asset. Okay? So what is this? This is risk. This is expected return. So many times we will use this way of illustrating things. This risk expected return space. Okay? We have one asset. The first asset, F, the risk-free asset, gives us a certain expected return for zero risk. Okay? We have the risky asset. The risky asset gives us another expected return for a certain level of risk. Okay? So what you can already see is that, remember we said risk-averse investors are only willing to consider risky assets if the risk premium is positive, right? If there is a positive risk premium. If they get more expected return for taking the risk. Which seems to be the case here, right? Because the expected return for P is higher than the expected return for F. So theoretically, even the risk-averse investors who don't like risk, they would consider P because it gives them some benefit over F, some more expected return, a risk premium. So, are these all possible investments in our two-asset world? Right. Obviously not, right? Because now we can combine F and P. And where are all the combinations of F and P? Where are the risk-return combinations of the portfolios that consist of F and P? Well, this is exactly the straight line. This is what we call the capital allocation line. So the capital allocation line shows us the possible risk-return combinations in this universe. So every point on the capital allocation line is a specific portfolio that consists of F and P. And then the point on the capital allocation line in this space shows us the expected return and the risk for this portfolio. Right? So this is what we kind of already talked about last week. So these things are quite important because we will build up on them later today. So if there is anything that is unclear here, what this means or what this line stands for, please let me know. So what does point A represent? Well, just any portfolio, approximately half F, half P. And because this world is relatively simple, we have a linear relationship for risk and for return. I mean, everything is on a straight line, so things are relatively simple, right? Good, so this would be approximately a portfolio that consists of half F and half P. So then, kind of strangely, when I plot the line, you could say, I did not stop at point P. I mean, at point, what does the point P represent? Point P represents the situation in which we invest 100% of our wealth in P. Everything we have is in P. Okay? So how can we then go beyond P? What do the points on the capital allocation line to the right of P, what do they represent? What is that? Borrow, leverage, yeah. You take a levered position. So basically what that means is you borrow money and you overinvest in P. We talked about that in Unit 1. This is exactly what buying on margin is. So these points on this bluish, darker bluish line here, they represent situations in which you invest, for example, 120% of your wealth in P. And this is possible because you can invest 100% in P and then you borrow another 20% and you also invest that in P. Okay? This all, of course, is here highly simplified in the sense that there are no frictions. And the second assumption, if you think about that here, is that what is the assumption about lending and borrowing rates here? So the implicit assumption here is basically that, I mean, if you think about F as a bank account, a savings account, the risk-free asset is just your savings account where you store your money and you get a return of, I don't know, 2%. Okay? So at point A, you would put half your money on your savings account and half your money in P. Right? So now if you move beyond P, you are not putting money on your savings account, but you're taking a loan from the bank, as you're borrowing money from the bank. And the assumption here is the assumption here is that the lending rate and the borrowing rates are the same. Because otherwise, what would happen if the lending rate and the borrowing rate are not the same? So let's wait with that for 1 second. Okay, what would happen if the lending rate and the borrowing rate are not the same? And the way to answer that is really think about the slope of the capital allocation line. So what is the slope of the capital allocation line? It's basically the risk premium, expected return minus the risk-free rate, scaled by the risk. So this, quickly go back. This is exactly this expression here. 8 divided by 22. So 8 is the risk premium, 15 minus 7, and 22 is the risk. So this is the slope of the capital allocation line. Risk premium divided by risk. Okay? So what would now happen if the lending rate and the borrowing rate are different? Right, the gradient changes beyond P. We don't get a straight line anymore, we get a kinked line. Right? Because if the lending rate and the borrowing rate are different to the left and to the right of P, the slope will be different and the line will kink at P. Right? I will show you in a second. We have the picture in the slides. Okay? So the slope of the capital allocation line, you can also call this the reward to risk ratio, or it's also sometimes, but yeah, it's something that is very closely related to the Sharpe ratio. So this slope of the capital allocation line is really very important because it shows you how much premium you get for taking risk. It's the risk premium scaled by risk. And now if you think about that, And this will become important later. I mean, two more questions, okay? First, what is the reward to risk ratio for P, A, and F? Which one has the highest reward to risk ratio? They all have the same, right? All points, all portfolios in this investment universe, all of them have the same reward to risk ratio. So all points on the capital allocation line, because it's a straight line, they have in this universe the same reward to risk ratio. So you cannot simply find the optimal portfolio by saying, oh, I want to find a portfolio that gives me the highest reward to risk ratio. That's nonsense because all portfolios have the same, right? So all points obviously on the capital allocation line, same reward to risk ratio. Second question, how could you make the capital allocation line better? So in other words, what do investors want to optimize? So if they could change the capital allocation line, do they want it to be steeper or less steep? Do investors prefer steeper or not so steep capital allocation lines? Well, obviously steeper lines, right? Because if the line is steeper, if the slope is higher, that means you get more reward for taking risk. So if we could change the capital allocation line to a higher slope, something like this, that would make our investor more happy, because then the investor could get more reward for taking risk. We will get back to that. So I'm a little bit jumping ahead here, but these are important concepts that we will use later today. Good. Yeah, so this picture, we know that. So this is in your slides. We will jump that. So pretty much everything we have on this slide we talked about. So there's a linear relationship between risk and return, and the capital allocation line shows you the possible risk-return combinations. We sometimes also call this the investment opportunity set. Okay, so yeah, just a term. The slope is called reward to volatility ratio, also reward to risk ratio, also sometimes Sharpe ratio, so there are different terms for this slope. The term itself isn't so important. You should remember what the slope stands for. The slope is risk premium scaled by risk. Okay? Yeah, some examples. What about borrowing? Yes, we talked about that. What happens if lending rates and borrowing rates differ in practice? Well, we also talked about that. It's not super complex. If lending rate and borrowing rate differ, then we have two different slopes of the capital allocation line, because the risk premium, which is the expected return of the risky asset minus the risk-free rate, that will differ to the left and to the right of P, and we will have a kinked line, something like this. Okay, but again, if you know what the slope of the capital allocation line is, I mean, this is absolutely trivial. Slope is risk premium by risk. So if the risk premium is different on the left and on the right of P, I mean, obviously the slope must be different. Okay, and economically, what that stands for, or what that means is, the reward to risk ratio, or the attractiveness, decreases after P, so because the slope is lower after P, which is caused by the higher cost of borrowing, right? I mean, suddenly you have to pay 9% for borrowing and 7% for lending. So this area here is somewhat more attractive than this area. Simply because lending and borrowing rates change. This is also, by the way, I think a nice example that a lot of the things we do here are very strong simplifications of reality. Obviously, I mean, a two-asset world is not even remotely close to what we see in real life. But a lot of these assumptions we can actually relax, and the basic message wouldn't change. Okay, so from now on, we will again use the assumption that lending and borrowing rates are the same. So we will have a straight line. But if we would relax that, I mean, you see that actually what happens is the line kinks, but nothing fundamentally changes. Okay, but obviously, using the simplification of same lending and borrowing rates gives us the straight line, and it will be easier to deal with that in the future. If you do calculations and stuff, it's always easier if you have a straight line, a linear relationship, instead of this kinked line. But economically, things wouldn't change dramatically if we would have different lending and borrowing rates. So in other words, you could easily incorporate that into the model without violating the model's general results. So the general results would still go through. It would just be more complex to do all the calculations. That's why we don't do it. So in some sense, what we try in the lecture is always to use the simplest possible world so that you can still see the effects, but in the most simple way. So just a bit of background why we use such strong simplifications. Good. Sorry. So that's what we have so far. The problem that we are still facing is that we don't know, that we don't know which portfolio on the capital allocation line we should optimally choose, right? We now know that actually these are all the possible portfolios on the capital allocation line, but we don't know how we can choose the optimal portfolio, right? I mean, that's what we ultimately want. We want to know for a specific investor, should this investor invest all in F, all in P, or in some combination of F and P? That's our final target. So how could we do that now? How could we find out the optimal portfolio for a specific investor? Any ideas? How can you now find the optimal portfolio? Remember, there is another thing that we spent quite a bit of time on last week, and that was the utility functions, right? So if you combine utility functions and this, I mean, how could we find the optimal portfolio? So what is the optimal portfolio? I mean, that is the portfolio that gives the investor the highest utility, right? So we have to find the portfolio that maximizes the utility for our investor. How do we do that? Well, we will see there are actually different ways to do that. So one way to do that will be the analytic solution. So we can now go and we can now simply say, look, this is a function, and in this function, we said we now use the utility, we have a utility function, right? I mean, that is what we already know from the last lecture. So the utility is expected return minus 1/2 A times sigma squared. I mean, that is the utility function we are using. Remember, I mean, that is what we developed last week. So now we take this utility function, set in the values for expected return and sigma squared for our specific world, expected return, risk-free rate, plus risk premium times y, and this simple relationship for risk. So we set that in. Here, expected return, and here risk. And then we simply maximize this function with respect to y. So y is the fraction we invest in the risky portfolio. Okay, y. How much we invest in the risky portfolio. And this is the function. So how do we maximize that? I mean, very simple. We find the first derivative with respect to y and set this to 0, and this will give us the maximum of the function. And this y will be the y that maximizes utility for the investor. Okay? So this is what we then call the y star, the optimal y, or the y, the fraction in the risky asset that optimizes, maximizes the utility for our investor. Okay? So how do we do that? Well, I mean, this is quite straightforward. So here you have the different steps. Let's go through it very quickly. So again, this is the utility. This is the utility formula. We simply start with the formula that we had developed no, we haven't developed it. I told you that this is the utility formula that we will use for this lecture, right? Expected return minus 1/2, this one, minus 1/2 a sigma squared. So this is just something that is given. Then we set in the values for our specific world. So this is expected return, and this is the risk in this specific world. And then we try to find the first derivative with respect to y. So what is the first derivative here? Well, this RF term that drops out because there is no y in it. The second term, we have y times this bracket term. So basically the y goes away and the bracket term stays. So this is here. And in the last term, we have y squared. So the first derivative of y squared with respect to y is, of course, 2y. So we have 2y here. Okay? 2y, and then we just marginally simplify this thing. 2 times 1/2. Then we set it to 0. Very simple, set it to 0. We just restate a little bit. And we get y equals ERP minus RF divided by a times sigma squared. Okay? So from here it's really just restatement. So let me go back one slide because there we can see it a bit larger. What is now the economic interpretation of that? Or in other words, does this make any sense? Well, this tells us that the optimal fraction that we should invest in the risky portfolio increases with the risk premium. So if the risk premium is higher, we should, all else being equal, optimally invest more in the in the risky portfolio. Okay? Does this make sense? Yeah, kind of, right? Because if you get more benefit for taking the risky asset, I mean, everything else being equal, you will invest more. If the risk premium is 0, so if this here is 0, then you would not invest in the risky asset, right? Because then the fraction, if this here is, this term here is 0, then y star would be 0. Okay? Which makes sense. We said the risk-averse investor would only be willing to consider the risk-free asset. A risk-averse investor would only be willing to consider the risky asset if she gets a premium, if the risk premium is positive. So y star increases with the risk premium and y star is higher if A is lower. So if A goes up, then y star goes down. There's an inverse relationship between A and y. Again, that makes sense because if I'm more risk averse, I will, all else being equal, invest less in the risky asset. And the same is true for risk. If the risky asset is more risky, if sigma squared p is higher, we will invest less in the risky asset. So you can now also see something that is important to realize here, to keep in mind also for later. This, sorry for jumping a bit, this capital allocation line, this is the investment universe, and this capital allocation line applies to all investors in this universe. So if we all live in this very simple two-asset world, I mean, this is our capital allocation line. So this applies to all of us. Now, however, each and every one of us will choose a different point on this capital allocation line that maximizes his or her utility. Okay? And this point, the optimal complete portfolio, how much F and how much P you prefer, this depends on A. So this is the investor-specific level of risk aversion. So the A here is the reason why all of us will have a different complete portfolio in this world, right? Because you might have a higher or lower A than I or your classmates. So you will have a very specific combination of F and P that maximizes your own utility. Okay? Clear? Good. So this is the analytic solution. Okay? But I mean, the analytic solution suffers a bit from the fact that it's sometimes a bit hard to really see what's going on because it's just a formula. So let's approach the problem a bit more slowly by starting with an alternative to the analytic solution. So instead of finding the first derivative, setting it to 0, there could be another way for you to identify the optimal complete portfolio. And this other way is just like brute force calculating utilities. Okay? So you could say, well, you need to know your level of risk aversion, let's say it's 4. Yeah? And then for specific y's, so for specific fractions in the risky asset, you just set in the values and then you get expected returns. If you use the expected return formula, you get the risk of the complete portfolio if you use the risk formula, and then you set in expected return and risk in the utility formula, and you get your utility. So very simple. It's really just these three formulas: expected return of the complete portfolio, risk of the complete portfolio, and utility. You set in the values and that's it. And then if you plot that, I mean, it already gives you some indication where your optimal portfolio allocation would be. So this is the utility that you get, and this is y. So this is calculated in discrete steps of 0.1, 10% steps. So of course this is not super precise, okay? But you can already see if you start at 0y, so that means only risk-free asset, your utility is exactly the risk-free rate. And then you add a little bit of the risky asset, so your utility goes up, and you add more, it goes up, it goes up, it goes up, but at some point it declines again. So it seems your optimal utility will be somewhere around 0.4, around 40% risky portfolio, 60% risk-free asset. So this is what you can see from this very simple, I don't know how you want to call it, but it's like really just setting in values in formulas and brute force calculating. Okay? Of course, I mean, this is calculated in steps of 0.1. You could make this more precise by using smaller steps, but it's very time consuming, so you wouldn't probably do it in practice, but you could. You could do this in steps of 0.05 or 0.001 or whatever you want. So this would also allow you to identify, the optimal risky portfolio. Not as precisely as the analytic solution, but a bit more intuitive maybe, or more illustrative. Yeah? So we have talked about two ways to find the optimal complete portfolio: analytic solution, brute force calculation. There is a third way, and the third way is a graphical approach, which will also not be very precise, but it will be nice in the sense that it offers us some insights. Okay? To do that, to do the graphic approach, let's start with something slightly different. And let's go back to something that we developed last week, and this is utility indifference curves. Okay? So for this specific investment world, we are now trying to define or to draw indifference curves for an investor. And actually, we are not doing this for one investor, we're doing this for two investors. One investor has a risk aversion of 2 and the other has a risk aversion of 4. So what is an indifference curve again? An indifference curve is a curve and all points on this curve, it's a curve in the risk-return space, in the same space that we now use all the time. And all points on this curve offer the same utility to our investor. Right? All points on the curve offer the same utility to our investor. So how can we now draw that? Well, it's relatively simple. We can, for example, define that we want to draw a utility curve that offers a utility of 0.05 for this first investor. And then for every level of risk, or for different discrete levels of risk, I mean, we just randomly choose the levels here, or the steps, we calculate the expected return that this investor needs to achieve that utility. So, I mean, what you do is you simply take the utility formula, rearrange it, and solve for expected return. So what this now tells us is that all these risk-return combinations, a risk of 0.1 and a return of 6%, or a risk of 0.4 and a return of 21%, all of those, they're equally attractive to our first investor, and all of them lead to a utility of 0.05. So if the same investor wants to achieve a higher utility of 0.09, I mean, we can do the same exercise, and obviously, then for every level of risk, this investor needs to have a higher expected return. Right? That would give him or her a higher utility. We can do the same thing for a second investor with a higher level of risk aversion. Same approach. And then there are some things that are interesting to see. So for example, for a given level of risk, let's say 0.2, the first investor requires an expected return of 9% to get a utility of 5, of 0.05. 9%. If we go to the more risk-averse investor, the more risk-averse investor requires a utility of an expected return of 13% to achieve the same utility. So the more risk-averse investor demands more expected return for the same level of risk so that she ends up at the same utility. And this is simply because she dislikes risk more and wants more compensation for taking risk so that her utility would stay the same. Okay? So this is just like a numerical example of something we did last week, and if you plot it, it looks like this. And you remember I showed you last week the plots for different indifference curves for different types of investors. What's the shape of the indifference curve for the risk-neutral investor? It's a horizontal line, right? Risk-neutral guy, horizontal line, because the risk-neutral guy for a specific level of expected return always gets the same utility, because this guy doesn't care about risk. Now, if we have risk aversion, if we have risk-averse investor, their indifference curves are not horizontal lines, but they are these curves. And the slope of the curve indicates the level of risk aversion. If the slope is higher, this indicates more risk aversion, right? Why? Because if we increase risk and the slope is higher, this means that now we need much more compensation in order to end up at the same utility. This is what we talked about last week, okay? Clear? Good. So, now, let's slowly combine indifference curves and capital allocation lines. Okay, so this is the capital allocation line. This is exactly what we had before. So if we now plot the indifference curve for a specific investor, so this is a specific investor with A equal 2. Right? Remember, indifference curves are always investor specific because their slope depends on risk aversion. So all of us, like, I don't know, we are probably 30 people, we would have 30 different indifference curves. Okay? So this is the indifference curve for a specific investor. Yeah? So how can we now use these indifference curves approach or this graphical approach to find the optimal complete portfolio? Any idea what we could do? Which indifference curve maximizes the utility for this investor?
One that is tangent.
Right. One that just touches the capital allocation line in a tiny single point. Because if you remember here, as you can see, higher indifference curves, and that is also what we talked about last week, higher indifference curves always go along with higher utility for risk-averse investors, right? Also for risk-neutral. If the indifference curve is higher, like the two blue lines are the same investor, but the higher one has a utility of 0.09 and the lower one of 0.05. This is what I just said. I mean, higher means you get more expected return for a given level of risk. This always leads to more utility. So if we want to maximize utility, we have to find the highest possible indifference curve. Right? Higher indifference curves, higher utility. So we could say, oh, this is a great utility indifference curve. This is a utility of 0.5 and this 0.05 and this is 0.15. This indifference curve would be amazing. It would be a very high utility. Right? What's the problem with this indifference curve? Obviously, it's not possible, right? I mean, all the possible risk-return combinations in the whole universe, in our world, are on the capital allocation line. This risk-return combination is not available. This is not available. This is not available. This, nothing's available. The only possible risk-return combinations are on our line here, on our capital allocation line. So then, as you correctly said, the indifference curve that is as high as possible and as high as possible, which is still, and we are still able to invest along that, which is still realizable in our world, is the one that touches the capital allocation line in one single point. So this will give us the highest utility. And what do? Well, we invest in the tangency point here. So this would be the optimal complete portfolio. So this, by the way, is an illustration, and the numbers don't match 100% with the example, but yeah, it's for illustrative purposes. So the the illustrations on your slides match better with the numbers. This is, I think, probably, I hope, more illustrative. But don't look at the numbers too closely. Okay, so this 0.1 indifference curve, this gives us the highest possible utility. And how can we achieve that? Well, we can achieve it by investing exactly in the tangency point. If we move this only a tiny bit further up, there is no possibility to invest in that anymore, because then it doesn't touch the capital allocation line. If we move it down, well, it's less attractive because it's further down, so the utility is lower. Okay? Graphic the solution. So those are the three solutions, how we can find the optimal complete portfolio. Analytic solution, first derivative equal to 0, pretty simple. Brute force, we just calculate for discrete steps of y. Yeah, time consuming, not very precise, but a first step to identify the area in which the optimal y will be. Third solution, graphic. Plotted indifference curves, find the indifference curve that is as high as possible, but still touches the capital allocation line. So now you can also again nicely see why different investors have different optimal portfolios C, because what happens if we introduce a second investor here, the second investor has a higher level of risk aversion. Well, the second investor will have, again, don't look at, the numbers are a bit made up, but the second investor will have a different shape of the indifference curve, steeper, and because of that, there will be a different tangency point, and because of that, there will be a different optimal complete portfolio for our second investor. Okay? Every investor will have her own optimal complete portfolio C, a unique combination of F and P. Is that clear? Good. So yeah, this is the more precise illustration for the numbers that we use in this example. So these are exactly these are four different indifference curves, and the higher we go, the higher the utility is. And yeah, as I used it in my illustration, the straight black line, this would have the highest utility, but unfortunately the straight black line is not possible because it never touches the capital allocation line. So the highest indifference curve that still touches the capital allocation line is this dashed blue line, and the utility is 0.08653. Okay? It's the same thing as I just showed you, but with the correct numbers for this example. Then you can also do that, the whole thing, you can calculate everything. So we can calculate now expected returns for these different indifference curves, so as we did it before. So for every level of risk, for a specific investor, we calculate the expected return so that the utility equals 0.07. So this is basically calculating the indifference curve. Then we do the same thing for a slightly higher utility, again, higher utility, higher utility. And then we can also calculate the expected return on the capital allocation line for a given level of risk. So, and this is the table illustration of this here. I mean, what you can see is that, of course, this highest utility, I mean, that would be most preferred, but the expected return for every given level of risk is always higher than what we have on the capital allocation line. So none of these points will be able to be, we will not be able to realize any of these points because we would always require a higher expected return than is possible in our world. If we move one utility level down, and these are randomly chosen numbers, of course. I mean, you could use 0.093 as well. So this is just chosen for illustration. If we move one utility level down, I mean, we do the same thing, and now, bam, we find that there is one expected return that exactly matches the capital allocation. So this would be the tangency point. Of course, identifying the tangency point precisely using this graphical solution would be pretty hard, but that's not the point. I mean, I think the graphical solution is useful because it tells us something about the ideas behind the optimization problem. Good. Analytic solutions, yeah, I mean, this is what we developed, Y star, risk premium scaled by A times sigma P squared. So we can simply set in the values for Y star, so we get 41%. So an investment of 41% in the risky portfolio P will maximize the utility for our investor. So in this optimal complete portfolio, we get a Sharpe ratio of 0.36, a reward to risk ratio of 0.36. But as we said before, I mean, the reward to risk ratio for all complete portfolios is the reward to risk ratio for all complete portfolios, for all points on the capital allocation line is what? The same. Right? The slope is the same here and here. So the reward to risk ratio is simply the slope of the capital allocation line, and this would be the same for all complete portfolios in this universe. Right? Every point on the line, on a line has the same slope. Yeah. Last slide before the break. What is the risk-free asset? Yeah, we talked about that quite a bit. I will make this short here. So different ways, treasuries, money market funds. Nothing's really risk-free in reality, but short-term government debt, short-term money market funds are relatively close to risk-free. Is this one risky asset case reasonable? Well, to some degree, yes, and we will come back to that later. We will need that to really develop portfolio selection also in a more complex world. Because instead of thinking about it as one risky asset, you could think about it as a stock market fund. So you could think about the theory world here, one risky, one risk-free asset, as the problem that you have a risky stock market fund and you have your savings account. And now you try to allocate your money between your savings account and the stock market fund. So this is exactly what this chapter does. It tells you that the optimal fraction Y that you should invest in the stock fund depends on expected return, risk, and your level of risk aversion. Okay? So although the world is not realistic by itself, we can easily transfer it into a world that kind of makes sense. Good. So this finishes chapter 2, and after the break, we will do chapter 3. So 10 minutes break. Okay, so let's start with Unit 3. So Unit 3, first part, which will be what we do today, is optimal risky portfolios. So we are still talking about the Markowitz portfolio selection, but now we go beyond the one risky, one risk-free asset world, and we will actually think about a world that consists of two risky assets. So, of course, also a too risky asset world is not like a very good representation of reality. But at the end of today, I will show you that extending the too risky asset case to the multiple risky asset case is conceptually not very hard. Of course, it makes things more complex to calculate, but the ideas are the same. Good. Portfolio of two risky assets. So we talked about that a lot. Covariance and correlation will be important. So yeah, I will not repeat all of that. The terminology that we use, we will have the portfolio return. So RP is the realized return, which is just the weighted average. The portfolio return, the weight that we invest in the bond fund or in the bond, the weight that we invest in equity, and the return of bond and equity. Okay? So, and at the end, it really doesn't matter what these two assets are. So you can think about them as a bond and as a specific stock, or you can think about them as a bond ETF and an equity ETF or whatever you want. Just any two risky assets. So this is like directly going back to what we did in the portfolio statistics chapter. Expected return is the weighted average. We know that, very simple. Variance is not the weighted average. So the variance has this debt fund part, the equity fund part, and the covariance part. So this is exactly what we did in the portfolio statistics chapter. Again, it's not just the weighted average. And as silly as the example is, I mean, I think a good way to really always remember and illustrate that for yourself is this ice cream and umbrella store. So if you have the ice cream store and the umbrella store stand alone, they're both pretty risky. But now if you combine them in a portfolio, the portfolio risk actually decreases. Why? Well, because of their covariance structure. They have negative correlation. Yeah, so this here, don't spend too much, this is not so important now. This will become important when we talk about the capital asset pricing model, okay? So the only thing that this here says is that you can write this variance formula in a different way, which is mathematically 100% equivalent. So in this different way is that instead of WD squared, I mean, you write WD, that's obvious. But instead of the variance, you can also write the covariance of RD with RD. Why? Well, what's the covariance formula? The covariance is the variance of the first element times the variance of the second element times the correlation. So if you take the covariance of RD with RD, I mean, that's a correlation of 1 because it's the same asset, and then it's the standard deviation times the standard deviation, which is the variance. So this is why mathematically this and this is equivalent. Exactly the same. Don't get confused about that here. You can ignore that for now. We will actually use that, or I will get back to that when we talk about the capital asset pricing model. Okay? Good. Covariance. Covariance, again, is the standard deviation of the first asset times the standard deviation of the second asset times the correlation coefficient between the first and the second asset. So I think generally speaking, if we think or talk about co-movements, it's often easier to talk about correlations compared to covariance. And the reason is that covariance combines both the volatility or the movement or the risk and the correlation. So if we are purely interested in the co-movement structure, it's often easier to look at the correlation, also because the correlation has this nice feature that it is bound between minus and plus 1. So minus 1 and plus 1 are the both extreme cases. So what does a correlation of plus 1 mean? Well, this means that if the one asset goes up, the other asset always also goes up. And if the one asset goes down, the other asset always also goes down. But be careful, not necessarily by the same amount. It's just the same movement, the same directions. It could be that one asset goes up by 1% and the other goes up by 5%. So the correlation of 1 does not tell you that the movement is exactly 1-to-1. It's not plus 1% one asset, plus 1% second asset. It's just meaning that one asset positive return, the other asset also positive return. Okay? So what does a correlation of minus 1 then mean? Well, exactly the opposite. Correlation of minus 1 means one asset goes up, the other goes down, always. But probably not by the same amount. Right? One asset could go up 2% and the other asset goes down 7%. I don't know, something like that. Right? Minus 1, always opposite movements. Plus 1, always same movement. But the magnitudes might be different. Clear? So let's think a bit about the extreme cases, because there is actually quite a bit we can learn from them. What happens if the correlation is 1? What happens to our portfolio variance? And the next slide shows you the calculation. Actually, I think this is something that is really worth remembering, because if people get confused about diversification benefits and variances of portfolios, it's really valuable to think about the plus 1 case. So what happens in the plus 1 case? So perfect positive correlation. Of course, not a very realistic case. In reality, things are barely ever perfectly positively or perfectly negatively correlated. I mean, the highest correlations we can measure are probably 0.98 or 0.99 or something. Even two assets like the US dollar and the Hong Kong dollar, if you measure their correlations, they are not 1. Because the Hong Kong dollar has some window and is allowed to fluctuate around the Hong Kong dollar for a tiny bit. It's not perfectly fixed. There is a small bandwidth, a small window at which the Hong Kong dollar is allowed to fluctuate around the US dollar, which would already destroy your plus 1 correlation. So even for things that are packed, in reality you don't see a plus 1. But that doesn't matter. Conceptually, theoretically, the plus 1 case is still interesting. And in reality, we see assets that are highly correlated. 0.98, 0.99, 0.95, something like that. Okay? So what happens? So this is our general portfolio variance formula. Equity part, debt part, and the covariance part. But instead of the covariance, I mean, this is normally the covariance, but instead of the covariance, we can write the standard deviation times the standard deviation times the correlation. Right? Good. I mean, obviously, the correlation drops out because it's plus 1. So correlation, we can just ignore that. It's plus 1. So it's essentially this term here, the 2WD, WE, sigma D, sigma E. And the correlation is gone. Okay? So now if we look at this expression, and if you look at it carefully, you can see that this again is a binomial formula. It's the A term plus the b term plus 2a, a, the e part, and b is the d part. So this is a squared plus b squared plus 2ab. So we can simplify that by writing a plus b squared. Very simple. I mean, this is basic math. So this a part, b part, if you would spread it out, it's a part squared, so this is here, b part squared, this is here, 2ab, so this is 2, this is ab, and this is exactly this here. Okay? So, yeah, we have squared here, we have squared here, so we can get rid of it, no problem. So then we know the standard deviation of the portfolio is actually just the weighted sum. Right? That's the weighted sum of the standard deviation. Weight equity times standard deviation equity plus weight depth times standard deviation depth. And what you can now clearly see is what actually diversification benefit means. For the extreme case of +1 correlation, the standard deviation of the portfolio is the weighted average, just as the return. But for all other cases, the standard deviation of the portfolio must be lower than the weighted average. Why? Well, because because the correlation here cannot get above 1. So this is already the max. If we have something lower here, like 0.8, I mean, the whole expression is smaller. Right? The value of the expression must become smaller if we replace 1 by something that is less than 1. And if we do that, I mean, we would end up a term that is not as nice as this one, but it must be lower than this one. This is the upper bound. So the upper bound is the weighted average. And for all other levels of correlation, actually we get a standard deviation of the portfolio that is below the weighted average. And this is something that is called the diversification benefit. And I think sometimes people get confused because if you look at the portfolio variance formula, it seems like there is an additional term in addition to the weights, to the weighted average or something. But this is a misperception. This is because of the square terms here. Okay? If you really do the calculations, you can see that it's the weighted average, it's the upper bound for the only for the case of a perfect positive correlation. All other cases must have a lower standard deviation. And this is exactly the diversification benefit, that your standard deviation decreases because of the non-perfect correlation between two assets. Okay? So, of course, this is a highly theoretical case of +1, but it's still very nice to see that this is the upper bound. Okay? Upper bound. Realistically, everything will be below that. Yes. Okay? Clear? And now it's also absolutely clear, and you don't have to memorize stuff, you just have to understand that. You don't need a negative correlation to achieve a diversification benefit. As soon as the correlation coefficient here is not 1, I mean, this expression will be lower, and it will be below the weighted average. Right? Even a 0.99999 correlation between two assets gives you some diversification benefit. Of course, the diversification benefit, or by how much the standard deviation goes below the weighted average, that depends on the correlation. And the lower the correlation, the higher the risk reduction is. But there is some level of risk reduction for any correlation below 1. So conceptually speaking, as soon as you go below 1, there is a benefit. Okay? Clear? Good. So what happens if we have a perfect negative correlation? So second extreme case, perfect negative correlation. If you have a perfect negative correlation, there is something interesting that happens. And this is that now it is possible, or it must be possible, to form a riskless portfolio of those two assets. Right? Because if you know you have two assets, and they always move in exactly opposite directions, it must be possible to form a portfolio that has no risk. Easiest case, they always move by the same level, so they have the same standard deviation. That just means you invest half in the one asset and half in the other asset, because then one asset goes up 2%, then the other asset goes down 2%. Or the first asset goes down 5%, the second asset goes up 5%. So that would be completely riskless. Your portfolio return would always be zero. Okay? It's not that easy in reality, because I mean it can, obviously the standard deviations of the two assets in reality will not be exactly the same, likely. So we need to do a bit of calculations on how we can actually construct this riskless portfolio. But I think the idea is pretty obvious. If the correlation is -1, we have a guarantee of exactly opposite movements. We just don't know the magnitude of the movements. So that's why we need to do a bit of calculations, but it will be just like 3 lines, very simple. So we have a correlation of -1. So if we set in -1 into our portfolio, so we always start with the general portfolio variance formula. The first two parts are unaffected. The second, the covariance part, now covariance drops out, right, because we write it as standard deviation times standard deviation. Then the correlation is -1, so we have the 1 here and the minus here. So we have the minus sign here. And yeah, it's very similar to before, but now it's not a plus b squared, it's a minus b squared. So a term, b term to a term, b term. So it's a minus b squared. So we take the square root from both sides, very simple. So then we set this to 0 because we want the standard deviation to be 0, because now we want to know how we can construct the risk-free portfolio. So the risk-free portfolio by definition has a risk of 0. It has a risk of 0 if this term is 0. And if we solve this, I mean, it's not simple, it's not complex, it's just like 2 lines or so. If you solve that for WE, you find that WE, the weight that you have to invest in the equity fund, is sigma D divided by sigma D plus sigma E. Okay? So if you invest in the equity fund according to that expression, for the case of a perfect negative correlation, the resulting portfolio will have a variance, a standard deviation, a risk of nothing, of 0. Okay? So you can also see it kind of makes sense. You invest more in the equity fund if the debt fund moves a lot. If the debt fund is very volatile and goes up 5, -5, +5, if the debt fund has a high magnitude of the movements, then you have to invest a lot in the equity fund so that you can counter these movements. Like let's say the debt fund has high movements and a high sigma D, and the equity fund has low sigma D, then this would mean that the debt fund goes up 5% and the equity fund only decreases -1%. Right? So you need to have 5 times as much equity fund as debt fund to reach 0. That's the intuition behind that. If the debt fund moves a lot, high volatility relative to the equity fund, we need to have a lot of equity fund in the portfolio so that we achieve 0 total movement. That's the intuition. I mean, mathematically, it's very simple. You just solve and set it to 0. Okay? Good. Clear? So, generally speaking, what we see now, +1 correlation case, no risk reduction. Standard deviation is just a weighted average. -1, the ultimate risk reduction, we can find a portfolio that is completely risk-free. So if we move from plus to -1, this risk reduction effect becomes stronger and stronger. Okay? But it also exists for 0.999. Clear? So we will come back to these extreme cases in a second. So now let's do an example. Let's add some values to that. So let's say that the debt fund has an expected return of 8%, the equity fund has an expected return of 13%, and the standard deviations are 12 and 20. We assume a base correlation of 0.3, but we will actually change the correlation quite a bit. So what is the expected return of a portfolio that invests WE in equity and WD in bonds? Well, it's pretty simple, so we don't spend too much time on that. We now know that returns are linear, and it's actually quite boring in a sense. So if we invest all in the debt fund, so this W equity, if we invest all in the debt fund, well, we get the debt fund. If we invest all in the equity fund, well, we get the expected return of the equity fund. If we invest anywhere in between, it's just linear. Very simple. How can we realize points to the right of the equity fund here? So how would we be able to invest along this area? Yeah, there is only 2 risky assets. There is no bank, nothing else. But there are no frictions too. So it's a frictionless world. So here we invest 100% in the equity fund. Short? Yes. And 0 in the debt fund. If we move here, what we do is we invest 110 in the equity fund and minus 10% in the debt fund, which means we short the debt fund. Okay? Assumption here, no frictions, nothing, shorting is possible, there is no margin requirement for shorting, nothing like that. Okay? Frictionless world. And then you can realize points to the left and to the right of that, of the debt and the equity fund by shorting the other. Conceptually simple. Good. Oh, sorry. So I go over the return part quickly because after now we already know it's always linear actually. Let's spend a bit more time on the risk part. Okay? So what is the standard deviation of a portfolio that invests WE in equity and WD in the debt fund? Well, of course, this depends on the correlation between E and D. And what we can now do is we can, for discrete steps, we can calculate that. Okay, so we can say, look, we invest all in the equity fund, all in the debt fund, or in steps of 10%, we just go 10, 10, 10, 10, 10. And then for different correlations, we calculate the portfolio standard deviation. This is not magic, this is just setting it in the formula. So if you have an Excel spreadsheet, you can do that in 2 minutes. You program the formula, do it for different things, done. So if you do that, you can see a few things that are interesting. I mean, obviously, if you invest all in the equity fund, you always get exactly the risk of the equity fund. If you invest all in the debt fund, you always get exactly the risk of the debt fund. If the correlation is 1, actually it's a pretty linear decrease here. So now, interesting is not, what is interesting if we now look at the 50-50 case. 50-50 case, correlation of 1, then the standard deviation of the portfolio is 16%, which is just the weighted average of 20 and 12. Remember, +1 linear, just the weighted average. So, but now if the correlation, so we are here at 16, if the correlation is not +1, but the correlation is 0.3, actually the portfolio risk goes down to 13%. And if the correlation is not 0.3 but 0, the portfolio risk goes down to 11%. And if the correlation is -1, we even have a higher risk reduction to only 4%. So for a specific combination, and we are not changing the standard deviations of the individual assets, so the individual assets have the same risk, but if we change the correlation structure, actually the portfolio becomes much less risky. Okay? And now you can also see that for the -1 case, if you look at it, it seems quite likely that there is a point where the risk is 0. I mean, we don't exactly see the point because these are discrete steps, but risk is going down, 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 and here it's going up again. So the portfolio that is risk-free in the -1 case should be roughly 60% debt, 40% equity. Right? Okay? Good. So let's plot that. Let's again look at how, let's see how that looks like. So this is not our usual space, so be careful. This is not the debt, the risk return space. This is the fraction of equity. This is how much we invest in the equity fund, and this is the risk. Okay? So what is quite clear, I mean, we know the 2 points, I mean, debt fund and equity fund, I mean, that's obvious. What happens for the +1 case? How does the risk of the risk depend on the weight that we put in the equity fund if the correlation between the debt and the equity fund is 1? Any guess? +1 case, the boring case, it's just linear, right? It's just a weighted average. It's just a straight line. +1, then standard deviations, risk behaves like returns. It's just a weighted average. So if we invest half-half, well, we get just the average risk of the debt and the equity fund. Okay? Very simple. How about the -1 case? What do we know about the -1 case? What is special about that? The -1 case has the special feature that there is a unique portfolio with no risk. Right? The -1 case is special that there is a portfolio that actually has no risk. So we know there must be a point somewhere around here so that the resulting standard deviation is 0. Okay. So then it's quite logical to assume that also the other points are on these lines that connect E to this point and D to this point. So actually the risk is now a V shape. So if we invest all in the debt fund, and then we add more equity, there is a linear decrease until a certain point. And then after that point, there is a linear increase. And this point, again, don't look at the exact numbers, this point here is the portfolio that combines D and E so that the resulting portfolio has no risk. Clear? What about the 0 case? Or you could also replace that by 0.3 case. Well, if this is -1 and this is +1, I mean, it's kind of rational to assume that the 0 case is somewhere in between, right? Something like this. So we have not shown that formally here, but actually you can easily show it by just calculating it, and then you will see that it follows such a shape. So if you would, sorry for going back, if you would just plot this here, or this here, it would follow such a curved shape. So these are the 3 shapes we have. Again, this is not the risk-return space, this is the weight in the equity fund risk space. +1, linear. -1, V-shaped. Somewhere in between, like 0, we have this curve that is between the linear and the V-shape. Okay? So what this also shows actually is that even for like not extreme cases, even for a 0 correlation, it's actually quite possible that we can form a portfolio of the debt and equity fund, and the resulting portfolio here would have a lower risk than both the debt and the equity fund. So the debt fund has 12%, but you can form a portfolio of the debt and the equity fund, that only has a risk of 10.76% or 10.32%. And this exactly is the diversification benefit. So debt alone has 12%, equity is 20%. But if you form a portfolio, you can go down to 10.3. Even for non-extreme correlations of 0. You can go down to 0 for -1, obviously. Okay? Clear? So that will be important later. One quick remark just to avoid confusion here. Obviously, correlation is either 1 or -1 or 0. It cannot be all the 3 at the same time. So these are 3 completely different worlds. Okay? And we magically change the correlation structure between the assets in every world. Okay? So in reality, correlation is 1 number, and that's it. Okay? So this is a specific world, and in another world, D and E have another correlation, and then this is the result. So yeah, this is the same picture in your slides, so it's more precise. But you can see the -1 case, the +1 case, and the 0 and the 0.3 case somewhere in between. Good. So the amount of risk reduction that is possible, of course, depends on the correlation structure. I mean, it becomes more extreme if we approach -1. +1, no risk reduction, weighted average. Anything below +1, risk reduction. -1, optimal risk reduction, and there is a risk-free portfolio. The minimum variance portfolio, this is a little bit of a technical term. This is the portfolio that consists of the risky assets that gives us the smallest standard deviation, the least risk. When the correlation is -1, then the minimum variance portfolio has a risk of 0. Right? Because when the correlation is -1, we said it's possible to form a portfolio that has no risk at all. The minimum variance portfolio for the case that we have a correlation of less than 1. In this case, the risk of the minimum variance portfolio can be lower than the risk of either asset. Good. Let's take this one step further, and then we are nearly done with these spaces. Let's take this one step further and move it to the expected return risk space, because this is what we are ultimately interested in. We want to know how risk relates to return. This is always the key question for every investment. So what we do here is now we go to our usual space. We have risk, expected return. The debt fund has 12 risk and 8 expected return. Equity fund has 20 risk and 13 expected return. Okay? So far so good. So where are the possible risk-return combinations if we combine D and E? Of course, this will now depend on the correlation. So where are the possible risk-return combinations if we combine D and E? If the correlation between D and E is 1. What do you guess? Where is the investment opportunity set if we combine D and E for a correlation of +1? Yeah, just a straight line, right? I mean, risk is a straight line for this case. Return is always a straight line. It's always linear. So also the combination must be linear. So for the +1 case, it's just linear. So if the correlation is +1, I mean, this green line, and I stop at D and E here now for simplicity, you could also extend it beyond that. These points on the green line are the possible investments, the possible risk-return combinations in this world where the correlation is +1. Okay? Let's move to a different world, and in the different world, the correlation is -1. How does this look now? So what do we know? What is special about the -1 case? There must be one point with 0 risk. Right? I mean, that is what we developed so far. There must be some point that has 0 risk. So what we can relatively easily do, I mean, we can take the formula that we developed for that, we can set in the values, and we can calculate the expected return for this riskless portfolio. I don't know, somewhere here. Again, this is an illustration, this is not super precise, somewhere here. And then we just connect this point to D and E. So it's again a kind of 90% a lying down V. Okay? Okay, -1 case. So what you can immediately see here, but we are not yet interested in that, is that not all points in this investment opportunity set, not all of these points seem to be reasonable investment decisions. Some seem to be relatively stupid investment decisions. Right? Which points would be stupid investment decisions?
The point from B to the y-axis.
Right. Everything here. Right? Because we said the term for that is they are dominated by other portfolios. Right? For every level of risk here, I can find another portfolio on this upper arm that gives me a higher expected return. So this here is all dominated by other portfolios on this upper arm. But this will become important after the break. But for now, we are not interested in that yet. We are just looking at the investment opportunity set. So what are possible risk-return combinations without judging on their optimality or whether they are good or bad. It's just what is the possibility. Okay, so this is the possible investment opportunity set. And not surprisingly, now we move to the third case of a zero correlation. And as before, I mean, the result will simply be something between this lying down V shape and the linear relation. So something in between that, so something like this. Okay? So these points on this yellow curve, they now show the risk-return combinations of all the possible investments in this world where we only have the two risky assets D and E have a correlation of 0. There is no risk-free asset, there is no bank, there is no borrowing, there is no savings account, nothing like that. It's only those two risky assets. In this world, you can invest in D directly, you can invest only in E, or in a portfolio that consists of D and E, and then you get the points along this yellow line. And again, jumping a bit ahead, but it becomes quite obvious if you look at that now. Also here we have some portfolios that are not optimal. There are some portfolios that are dominated by other portfolios, right? Especially here, even point D itself seems to be quite stupid investment decision, because instead of investing in D directly, we could invest in a portfolio of D and E, and for the same level of risk, we would get much higher expected return. Okay? So this is the more accurate picture with the correct numbers in your slides. But it's exactly the same message that we just developed. So the blue line here points 3 correlation, the dashed blue line 0 correlation. Clear? Yes? So this, so far, is the two risky asset world. Yeah? And let me go back a second. In the two risky asset world, this is what we have. And we have to choose a portfolio somewhere on this curve. We will actually show that once we make this world a bit more complex and we add the risk-free asset, then also finding the optimal portfolio will become much simpler. So that's why we don't really talk about what is the optimal portfolio in the two risky asset case. We're kind of a bit lazy and skip this question. Okay? We simply develop the investment opportunity set, and then we say, look, these are the possible investments. But for this two risky asset world, we are not really talking about the optimal complete portfolio now. Because it turns out that in this case, for this world, this question is not so easy, because you can imagine now we have a curve, so there is no simple analytic solution for that, right? So we are kind of skipping that, but you will see after the break that skipping that doesn't lose any generality, because once we make the world more complex and once we introduce the risk-free asset, finding the optimal complete portfolio will actually become easier. Okay? So don't be confused. We are not looking for the optimal complete portfolio here in this world. For this world, our target was really to identify the investment opportunity set. Good. Let's have the break now. 10 minutes break. Okay, so last part for today. Any questions so far? Good. So we have now explored the diversification benefit, right? But we still only talked about it from a very mathematical point of view. So, I mean, we can do the portfolio variance formula, then everything else follows basically what we did. So we can see that combining assets in a portfolio reduces risk. I mean, this is all mathematically correct, okay? But what is the economic intuition? I mean, why is it actually that adding more and more stocks to your portfolio will likely reduce the risk? Well, the core economic reason is that there are two types of risks in the market. There is market-specific risk or market risk, and there is firm-specific risk. And the difference is very simple. Firm-specific risk only affects a single firm or a group of firms, but not the whole market. Market risk, contrary to that, affects all firms in the market at the same time. So market risk is also called the non-diversifiable or the systematic risk, and firm-specific risk is also called market risk is called systematic or non-diversifiable risk, and firm-specific risk is called the non-systematic risk. And it's non-systematic because it only affects a few firms. Okay? So let me give you a bit of an intuition of what we mean by a firm-specific risk. So firm-specific risk could be any risk that, for example, only affects a single firm. Like, I don't know, a factory burns down, or an employee steals some business secrets. So that would be a firm-specific risk. So what now happens to a what happens to firm-specific risk in large portfolios? Well, if you think about it, in large portfolios, firm-specific risks will not matter, right? Because let's say there is one firm and one firm suffers a lot because its factory burns down. Or let's say, I don't know, Toyota's factory burns down, so Toyota cannot produce cars anymore. I mean, if you only own Toyota, that's pretty bad for you, because Toyota will suffer a lot from that. But if you hold a large and diversified portfolio, and if you do not only hold Toyota, but also General Motors and Volkswagen and BMW and Tesla and all the other car manufacturers, actually you don't care, because as long as people buy cars, I mean, they buy no Toyota cars then, but then they buy cars from the other car manufacturers, and you also own the other car manufacturers. So there will be an offsetting effect. You will not suffer from this firm-specific risk of Toyota, because then the demand simply shifts to other firms, and they are also in your portfolio. So that's why in large diversified portfolios, actually firm-specific risk doesn't matter. It's completely diversified away. What cannot be diversified away is so-called market risk. So market risk is a risk that affects all the firms at the same time. So even if you hold a large diversified portfolio, you are exposed to that kind of risk. Okay? You're exposed to that kind of risk because, again, it affects all firms at the same time. So let me show you some risks or some news, and let's think about whether this is market or firm specific. So Fed could surprise markets with more interest rate hikes. Is this firm or market? Obviously, market, right? Toyota, Hyundai announced massive recalls of trucked SUVs. Obviously, firm, right? So then something like inflation. Inflation, obviously market. I mean, that affects, we see that a lot, or we saw that a lot in the past year. That affects all firms at the same time. even something like oil prices could be a market-wide risk because very many firms depend on oil prices, or that moves the market quite a bit. But then we have also clear examples of firm-specific stuff like Jérôme Kerviel, who kind of stole, he didn't really steal it, but he lost 7.2 billion for Société Générale because of the trading that he did. So that was very expensive for Société Générale. But of course it's firm specific, because even if Société Générale would have defaulted, I mean, as long as there is demand for trading and whatever, I mean, other banks would step in, and you as a diversified portfolio holder, you wouldn't really suffer from that. Yeah, and this is Deepwater Horizon, but examples of individual facilities burning down, like theft of business secrets, very firm-specific events. So let me show you a quick video that I think nicely summarizes or explains firm versus market-specific risk. And I will later tell you why this is really quite important.
Unsystematic risk is a company or industry-specific hazard that is inherent in each investment. Unsystematic risk is also known as non-systematic risk, specific risk, diversifiable risk, or residual risk. Examples of unsystematic risk include a new competitor, a regulatory change, a management change, and a product recall. A large restaurant chain has the unsystematic risks that new industry regulations will impact operations or food prices will escalate, hurting restaurant profits. These risks affect either the chain alone or the restaurant industry primarily. The chain also has the systematic risk that a recession or some other large economy-wide problem might cause virtually all stocks in the market to decline at once. Investors can greatly minimize unsystematic risk through diversification into other stocks or sectors, or other types of securities such as treasuries and municipal securities. For example, an investor holding restaurant stocks can lessen potential unsystematic risk by also holding energy, healthcare, and technology stocks. However, this will not remove the market-wide systematic risk of a recession or other economic downturn.
Okay, so this is really quite important. And this is now a bit of jumping ahead, but actually the capital asset pricing model is the central model in modern finance, probably, will have a very specific message, and the specific message of the capital asset pricing model will be that only market risk is compensated. So you can only expect to get higher expected returns if you hold market risk. Investors in competitive markets will not be compensated for holding firm-specific risk because it's so easy to diversify away. So if you do not diversify it away, if you hold it in your portfolio, what happens is that actually you have a relatively high risk, but you cannot expect to get a higher expected return for holding that risk because there is no risk premium for firm-specific risk. The capital asset pricing model will tell us there is only a risk premium for market risk. Okay? So that will be the central message of the capital asset pricing model. Yeah? Good. So, and before we move on, let me use this one example too, because I think this is really a nice example that summarizes the diversification effect. So this is how people, I don't know, 20 years ago rented movies. So they physically went to a store and took the DVD. Obviously that all is gone. So if you invested in such a company, and one example would be Blockbuster, like 20 years ago or so, I mean, you would have lost a lot of money. But that's a firm-specific risk at the end. It's technological change. So if you would have invested in the overall market, you would not only own Blockbuster, but you would also own Netflix. And over the time period when actually Blockbuster lost all of its business from 04 to 13. The blue, this is the revenue of Blockbuster. That is exactly the time when Netflix increased its revenues like crazy. So if you own both, you are fine. If you only own one, it's pretty risky. Okay? So I think this is a nice example that shows where actually this diversification effect that we mathematically derived, where this is coming from in real life portfolios. So if you think about, again, investing and the risk of portfolios, what we know is that the more stocks you have in your portfolio, the further the risk is reduced. But how far risk can be reduced in markets really depends on the market risk. So panel A here is like an not very realistic case, assuming that there is zero market risk. So in panel A, we assume that all the risk is firm specific. Okay? If all the risk is firm specific and you add more and more stocks to your portfolio, what actually happens is that you approach zero risk. For the more realistic case, if there is market risk and firm specific risk, what happens is that you add more and more stocks to your portfolio, and if then risk actually approaches market risk. So you completely diversify away the firm specific part, but you can never diversify away the market risk. Okay, again, because this is the risk that affects all firms at the same time. So your risk approaches market risk. And this is really why the capital asset pricing model will say, look, rational investors hold diversified portfolios. So they have no firm-specific risk in their portfolio, so there is no reason to compensate investors for firm-specific risk. So the only thing that will be compensated is market risk. That's the central message of the capital asset pricing model, but we will of course develop that slowly and clearly. So this is from a real life study. I think this is interesting, and this is, they looked at actually how many stocks you need to achieve a reasonable diversification effect. Okay? So if you only have one stock, of course you have quite a lot of risk in your portfolio. If you add a second stock, risk goes down. Third stock, risk goes down, 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 down. So, but this decrease in risk actually becomes smaller and smaller if you add more and more stocks. So what they find is that even if you have only 20 stocks, I mean, your risk reduction, your diversification benefit is already quite pronounced. So if you go from 20 to 100 stocks, I mean, there is not a lot of further risk reduction. A little bit, yes, but not a lot. If you go from 100 to 1,000, there is nearly no risk reduction anymore. So the message here is really, you don't need thousands of stocks to diversify firm-specific risk away. You probably only need 20, 30, 40, 50, something around that. Okay? Clear? Good. So, next step. We now make our world more complex, but we will see that it, in some sense, makes our life easier. We are now moving to a world that has our two risky assets, and additionally, we will have a risk-free asset. So what this basically means is we combine the first world, risk-free plus risky, and the second world, two risky assets. So our third world will be a combination of world 1 and world 2. Yeah? So we have a world with two risky and one risky assets. So everything else will be the same. So you can think of the two risky assets as a bond fund and a stock fund. The risk-free asset is truly risk-free with a standard deviation of 0. And we want to know what is the optimal, the investment opportunity set first, and then we want to understand what is the optimal complete portfolio in this world for our investor. Okay? Good. Let me skip that for a second. I'll come back to that. Okay, let's do that first. So this is what we just had. Right? This is our investment opportunity set, ignore F. This is our investment opportunity set in our two risky assets world. D and E, and here the correlation was, I don't know, 0 or something. It was not one of the extreme cases, it was around 0. So in the world without the risk-free asset, so F doesn't exist, these points on the yellow curve, they represent the investment opportunity set. Okay? So now in our new world, we magically introduce our new asset F, which is the risk-free asset, which means obviously it has 0 risk and some non-zero or some expected return. Okay? So now we can invest in what? We can invest in any point along the yellow curve, including D and E, or we can invest in F. Right? What else can we do? Is this now, are we now already showing the investment opportunity set? What else can we do? We can invest in F, we can invest in any point on the yellow curve. What else? Any ideas? Well, we can combine, let's say A is a specific point on the yellow curve, right? So A is a specific risky portfolio, a combination of D and E, right? I mean, that's what we talked about so far. So now let's say you want to invest in A. This is your risky portfolio. It's not probably the most rational choice, as you can see, but for some reason you like A. So you want to invest in A as your risky portfolio. So what can you now do? Right, you can now combine A and F, right? I mean, if you think about A as one specific risky asset, ignoring everything else, go back to our first world, I mean, then we just introduced the capital allocation line. That's the same thing we had in our first world, right? A risky asset, a risk-free asset, so we can invest along the line that connects both. That is what we call the capital allocation line. So now in this world, we only have 3 assets, 2 risky and 1 risk-free, but you already see there are numerous different investment opportunities. The investment opportunity set becomes like incredibly large, because now every risky portfolio can also be combined with the risk-free asset. Right? We can easily think about a second risky portfolio, B, which is, I don't know, 70% E and 30% D. Again, we can combine the risky portfolio B with F and have a new capital allocation line. Right? We can find numerous investment opportunities here. So now it really makes sense to think a bit about optimality, because we need to reduce the complexity of this problem. We cannot simply show all the possible capital allocation lines, because then everything would just be blue here. Right? Basically every point here, everything here is possible. So if you think about optimality, let's first think about capital allocation line A versus B. Which one is better? You like A or B more? Who likes A more? Nobody. Of course, B is better, right? Capital allocation line B is better. It has a higher slope. It gives us more expected return for risk. That's the reward to risk ratio, if you remember. We always said, like, steeper, higher slope, more reward for risk, investor is more happy. Investor is more happy. So capital allocation line, stupid, nobody would do that. Everybody would prefer capital allocation line B over capital allocation line A, right? So now would it be possible to find another capital allocation line that is probably even better than capital allocation line B? And the answer, if I ask it like that, is obviously yes, right? So what is the optimal capital allocation line? What is the best capital allocation line in our world? The tangent line, right? So we have to find the tangent point, the tangent line, that's the capital allocation line. That will be ideal for everyone. That's the highest possible capital allocation, not the highest, that's the capital allocation line with the highest slope. The best reward to risk ratio that is possible in this world. I mean, of course, we would love to have an even higher slope. But this capital allocation line, yeah, this is just not possible. I mean, we cannot invest along that because there is no risky portfolio that is on this capital allocation line. So the capital allocation line with the highest possible slope in this world is the tangent line to this yellow curve from the risk-free asset. Every other capital allocation line will have a lower slope and be less attractive. Okay? So you can easily see that for every level of risk, capital allocation line P gives us the highest expected return. So what is the capital allocation line P? Well, the capital allocation line P is very simple. Sorry. It's the combination of the risk-free asset and one specific risky portfolio P. P is just a combination of D and E, and P was defined as the tangency point. So P is kind of determined by pure math. I mean, it's the tangency point here. And what is now really nice for us, what makes our life now relatively simple, is that we can safely ignore all the other capital allocation lines. And we can even ignore all the other portfolios. Because every investor who is rational, and we assume rationality here, will only invest in the risky portfolio P. Because only investing in P allows the investor to invest along capital allocation line P. So nobody would invest in D directly, in E directly, nobody would invest in A, in B, or in any of these other points. So the nice thing now is we know that only P is optimal. So actually now the world is again reduced to a very simple world, a world where we have F and P and one capital allocation line. We can ignore everything else. And then it will be very easy to also find the optimal complete portfolio, because that's the same problem we already solved today. The three ways, analytic solution, graphical solution, calculations, it's the same problem. We can ignore all the other risky portfolios. We only look at F and P and the capital allocation line. Actually, we move back to a very simple world, use the optimization that we developed in the simple world, because this applies one-to-one also in this world. Okay? So that's basically the Markowitz portfolio selection idea. Yeah? There is an optimal risky portfolio P. This portfolio is optimal for every investor because it gives every investor the highest reward to risk ratio. And then every investor will invest along the capital allocation line P. Obviously, which point on this capital allocation line you choose, I mean, that will depend on your risk aversion, right? I mean, that is what we saw so far. The complete portfolio will be different for every investor, and the complete portfolio will be somewhere on this capital allocation line. We will come back to that, but I think, so this, understanding this is really the key. I mean, then everything that follows is like really simple. In this chapter, at least. So is that clear? Good. So let me show you, I think it's easier to show it here. This is what you have in your slide. So these are the capital allocation lines. So basically that's the same that we just developed. And then this just describes the capital allocation line, but I think we now know what a capital allocation line is. So you can take a look. So this is, sorry. Optimal risky portfolio, the slope of the capital allocation line, the Sharpe ratio, reward to risk ratio, risk premium scaled by risk. So we want to have a slope that is as high as possible. So we maximize the Sharpe ratio, we maximize the slope. Graphically, that's very simple. That's the tangent line. Analytically, you can also do that. So you basically, the problem is you maximize this the slope under the condition that the weights equal up to 1. So you, yeah, that's, but this optimization, I mean, we don't do it. It's a little bit complex to really do the calculation. And it's honestly also not super important how exactly that looks like. It's more important that you understand where this is coming from. You try to find the capital allocation line with the highest possible slope. Graphically, it's very simple to do that. Analytically, you can do the calculations, and then you get this expression. So if you invest in the debt fund according to this expression, this will give you the optimal risky portfolio P. Okay? So I don't expect you to memorize this formula, obviously. But this would allow you to calculate for the 2-asset case the optimal risky portfolio P. So then you have this picture, which is equivalent to what I showed you before in my illustration. You have the investment opportunity set for the 2 risky asset world. You have D and E, and every point on the black curve here is a specific combination of D and E. And then we fit the capital allocation line with the highest slope, so which is the tangent line, to identify P, and P is then the optimal risky portfolio. Okay? Good so far? Clear? Too fast? Too slow? So, and the next step, I will go through that quite quickly, because, I mean, you can already see, we can ignore all the other capital allocation lines, so we only have one risky portfolio that matters and one risk-free asset that matters. So if we now want to identify the optimal complete portfolio, we can go back to the slides for the one risky, one risk-free asset world, what we did this morning at the beginning, and it's exactly the same thing. I mean, this is the analytic solution. The optimal fraction that you invest in the risky portfolio is the risk premium of the risky portfolio divided by the risk times A. Exactly one-to-one the same thing. And an alternative way to develop that are those indifference curves. I also showed you that earlier today. So I will not repeat that. So again, 3 ways: analytic solution, graphic solution with these indifference curves, or you do the brute force attack approach and just calculate for every y the utility, and then you find the utility that is the highest. Okay? So what's important to keep in mind is that this optimal risky portfolio P, this optimal risky portfolio P, this is the same for all investors, right? I mean, when we did the optimization here, there was no investor-specific component. We did not talk about risk aversion or something. So P is the same for every investor. Every investor has the same optimal risky portfolio. What the risk aversion of the investor then simply determines is the point on the capital allocation line. And you can also see that mathematically, if you analytically derive the optimal risky portfolio, there is no investor-specific component in that expression. So this is only market-wide factors. There is no A in here. For the optimal risky portfolio for the optimal complete portfolio, of course, A plays a role. So every investor along this capital allocation line will choose a unique complete portfolio according to her level of risk aversion. Good. So we can do an example. It's really just setting in the values. So the optimal risky portfolio, if we set in the values of our example that we used before, in this formula, in the analytic solution for the optimal risky portfolio, we get that the weight of the debt fund should be 40%, which means the weight of the equity fund should be 60%. The expected return on this risky portfolio is 11%, and the standard deviation is 0.142. This is really just setting in the values. So we get the slope, the Sharpe ratio, as 0.42. So what is the optimal complete portfolio if we have an investor with a risk aversion of 4? Yeah, well, we know everything. The risk premium here is 11 minus 5 risk-free rate. So 11 minus 5 is the risk premium. The standard deviation here, we calculated here, and the risk aversion is 4. So Y star is 75%. So which means that this investor optimally invests 75% of her wealth in the risky portfolio P, which consists of 40% the debt fund and 60% the equity fund. Okay? So you can also illustrate that. So 25% is risk-free. So in this example, it's treasuries. 75% is risky, and the weights are 40 versus 60. Okay? I think this is quite simple. Obviously, if we have a different investor with a different level of risk aversion, the relative share of the treasuries would change. Right? If we have more risk aversion, treasuries would go up. But the optimal risky portfolio P, that would not change. It would always be 40% debt fund, 60% equity fund. Okay? The only thing that would change is how much we invest in the risk-free asset if we adjust the risk aversion. Right? Of course, if expected returns or some other market-wide factors change, expected return, if the covariance between stocks and bonds, the correlation, if something like that changes, I mean, then everything changes. And the optimal risky portfolio changes, and we have to do everything from zero. Because you can easily see if you calculate, the weight of the debt fund, I mean, all these parameters play a role. So the optimal risky portfolio depends obviously on the covariance structure, on the expected returns, on the risk of the debt and the equity fund. So if these things change, then also the optimal risky portfolio changes. But this is actually the nice thing is once we calculate the optimal risky portfolio P, we can use that for all different investors. So we have a one-time calculation of the optimal risky portfolio P, which is in a way analytic. And then if you're an investment advisor, you can use the same optimal risky portfolio for all your clients. And the only adjustment would be how much you recommend your client to invest in a risk-free alternative like a savings account, and how much you invest in this risky portfolio. The risky portfolio would be the same for all the clients. It's only changing how much of their wealth you recommend them to invest. This is called, and this will be on the last slide, this is called the Tobin separation. So the finding the optimal risky portfolio can be completely separated from investor-specific aspects. It's purely analytical. No risk aversion, nothing plays a role. It's purely analytical. The risk aversion only comes in the second step, which point on the capital allocation line you realize. Okay? Good. So, a lot of theory today. But we only have like one more step to go. And the last step will be to generalize the too risky asset case to n risky assets. Okay? So let me show you. It's relatively straightforward actually. Of course, mathematically determining everything will be more difficult, but it's relatively straightforward. So this is again expected return risk space. So what we have in this space are individual assets, but then obviously you can also form portfolios of those individual assets. So actually there will be, even if you only have I don't know, 50 risky assets, you will have millions of portfolios that you can form based on these risky assets. So in green you see those risky assets. So the most tricky part in practice of doing this Markowitz portfolio selection for a universe of risky assets, or let's say for only a couple hundred, is actually to calculate those expected returns and risks for those portfolios. Because what in the Markowitz model, what you need as input parameters to calculate the green dots is actually the expected return of every security, the risk of every security. That's fine. I mean, if you have 100 securities, you need 100 expected returns and 100 risks. But what you also need is the covariance between all the securities. So for every security, you need the correlation with every other security. So if you only have a couple hundreds, you easily have to estimate 100,000 or even millions of correlations. Because that's not one parameter per asset, but that's one cross parameter. Yeah? So for every asset, you need to know the correlation with every other asset. So that's why in practice, calculating these green dots is pretty challenging. Okay? Conceptually, theoretically, it's easy. If we exactly know the correlation, if we exactly know everything, I mean, then it's easy. I mean, computational, that's not intensive. That's not intense, but it's difficult to estimate all these hundreds of thousands or millions of parameters in data. And that is actually, and this will be the topic for next week, why people in practice often prefer something like the index model over this full Markowitz model, because the full Markowitz model is so difficult to estimate. Good. So we now need to kind of simplify this because we cannot deal with millions and millions of risk-return combinations. So what we simply do is we say, look, for every expected return, we now try to find a portfolio that minimizes risk. Okay? So for every expected return, we want to find a portfolio that minimizes risk, and this is what we call the minimum variance frontier. Basically this. So this is for every expected return, the portfolio that minimizes risk. Right? We can directly see that not all portfolios on this minimum variance frontier are good investments. Because similar to what we said before, only the portfolios on the upper arm here are efficient. All the portfolios on the lower arm of the minimum variance frontier, they are dominated by this efficient frontier. Right? I mean, if you go back, you would never invest in this portfolio because for the same level of risk, you can invest here. So this is what we call the efficient frontier. Efficient frontier, this upper arm. So, and then everything is actually exactly the same as before. Because the efficient frontier, I mean, that's the same curve structure that we had in the too risky asset case. So people only invest along the efficient frontier because the efficient frontier dominates all other risky portfolios. So we can ignore everything else. And then things become very easy. We have the risk-free asset. We again find the tangency, the tangent line. We have the optimal risky portfolio P, and that's it. Done. And risky asset case. So the optimal complete portfolio is then a portfolio somewhere on that. And you can find it graphically, you can find it analytically, however you want. So in practice, in reality, the hard part of estimating this thing is really to estimate this green line, the efficient frontier. Because to estimate this efficient frontier, you need to have all the covariances and variances and expected returns. But if you would have the perfect data, and if we would know the exact correlation and expected returns and risks, it would be easy. It's not complex, or when we can compute even with a cheap laptop and Excel, you could do it. The problem is really that you need to estimate so many parameters that we somehow are not sure if the result is still trustworthy if we use real life data. So that's the practical problem of that. Conceptually, you see, it's very simple. I mean, extending 2 assets to n assets, nothing really changes. It just becomes much harder to identify the efficient frontier here. But once we know the efficient frontier, the optimization problem is exactly the same. Of course, much harder, much longer equations. We need matrix, the matrix expressions in the formulas and stuff. But it's conceptually the same. Okay. So here you have this picture. So this is the efficient frontier, the upper arm here. The minimum variance frontier is the whole thing. And this is often called the global minimum variance portfolio. So this is the risky portfolio that has the lowest risk. The least risky portfolio, if that makes any sense. Oh, sorry, that was the wrong direction. Yeah. So this is the efficient frontier, minimum variance portfolio. And as I said, basically nothing really changes to our previous case. If we now include the risk-free asset, we again have the risk-free asset here. The capital allocation line is the tangent line. P is the optimal risky portfolio. That's it. So nothing new compared to our previous problem. Yeah? Same optimization as for the previous problem. Nothing changes. Once we identify the efficient frontier, we are exactly back to the too risky asset case where we have this yellow curve and then we find the tangent point and everything is the same. Because we can safely ignore everything else. We only have to look at the efficient frontier. Good. So everyone invests in P, regardless of risk aversion. Risk aversion only kicks in when we choose the optimal complete portfolio C, in the sense that less risk-averse investors put more in P and less risk-averse investors, more risk-averse investors more in the risk-free asset. Right? That is what we already know. And then the expected return and the portfolio variance formula. This is the way how to write them for the n asset case. So instead of using the expression we had before, we can use this expression using the sums. It's exactly the same thing. So theoretically, you can use these formulas to calculate the portfolio risk for a 1,000 asset portfolio. Okay? But again, for a 1,000 asset portfolio, you will need a lot of correlations. I will show you some numbers next lecture when we talk about the index model. But even if you only focus on one market like NASDAQ or so, you would need to estimate millions of correlations to estimate the Markowitz model in practice. The nice thing about the Markowitz model is really that it offers us a very clear conceptual way to think about this optimization problem. And in a theory world where we don't have to estimate things, where we know the correlation structure or we just assume a correlation structure, this is a very nice model. Okay? And this is actually the starting point of the capital asset pricing model. So the capital asset pricing model will start from exactly this moment when we say, look, the optimal risky portfolio is the same for every investor. This will be the core starting point and also the core assumption of the capital asset pricing model. Because the Markowitz portfolio selection model doesn't care about what are the general effects of that. The Markowitz portfolio model only cares about optimization in the eyes of one specific investor. The capital asset pricing model takes the idea of Markowitz one step further and says or asks, what happens to the overall market if every investor follows this recommendation? So this is how the capital asset pricing model starts. Okay? Yeah, I told you about this separation property. That's pretty nice actually in the model, that the determination of the optimal risky portfolio is purely analytical. So if we, in a theory world where we know everything, expected return, risk covariances, that's very simple. And then how much we allocate to the risky and the risk-free asset, this is depending on risk aversion. So the practical implication of that would be that investment managers would offer the same portfolios to all clients, as I said before. They simply adjust the fraction that the client should optimally invest in this risky portfolio and in a treasury or bills or savings account or whatever. Okay, so in reality, not totally clear if that's the case. Some investors might have investment constraints, but also different portfolio managers, they might actually estimate different optimal portfolios P. Because of course in reality, we don't know what is the true variance, what is the true covariance, what is the true expected return. So we have to rely on historical data mostly to estimate that. But if two portfolio managers use slightly different time series, one uses 5 years, the other one uses 10 years of data to estimate the Markowitz model, they would end up with different optimal risky portfolios, right? So in reality, if we estimate the model, I mean, it's not necessarily the case that everyone comes up with the same optimal risky portfolio. In theory, it is. In theory, everyone has the same optimal risky portfolio, because of course in the theory world there is no uncertainty about the parameters, they are just given. But this will actually be the key topic of index models, which will be the topic next week, how we can make the Markowitz model more applicable to real world scenarios. Okay? Thank you very much, and I see you next week.